Hi everyone, I am Kalmesh Yadav. I am an AI resident with the Habitat team at MedAI. And today I will be talking about a recently organized ObjectNav Challenge 2022. This work was done with collaborators at MedAI, Georgia Tech, Simon Fraser University, UT Austin, and Cornell. First, let me give you an outline of the talk. First, I'll talk about the ObjectNav task. Then I'll talk about our recently released HM3D SEM dataset, which we use for this challenge. Then I'll talk about the winners and do some submission analysis. This would be followed by a presentation from the winning teams, and finally I'll give some concluding remarks and maybe some next steps that we can have in ObjectNav. So let's start with the task. So let's say you have an agent that is initialized in a new scene randomly, and it is asked to navigate to this goal object. For example, in this episode, this goal object is +2. It is given access to RGB and depth information that is coming from a camera attached on top of the agent. And it's also given access to GPS and compass sensors, which basically tell it information about how much it has moved with respect to the start position and orientation. The agent is supposed to go to these goal locations, which are denoted by these red points on the map. And it is considered a success if it reaches within any part of this red region. Possible episode in the environment could look like this, where the agent starts from a location and it reaches this tool in front of it. Now, let's look at the embodiment for the agent that we use in this task. While the agent in itself is just a cylinder, we decide the dimensions of the agent using a real-world robot. More specifically, it's the Locobot that was released by Facebook a few years ago. The robot in reality looks something like this, and it has a base radius of 0.18 meters and a height of 0.88 meters, which are used to define the dimensions of the cylinder. We use 6 actions. These are discrete actions. The first action is move forward, where the agent is allowed to move by 25 centimeters. It's allowed to then turn left by 30 degrees or right by 30 degrees. It is also capable of looking up and down by 30 degrees. And the final action is stop, which the agent needs to take when it reaches the goal location. In terms of the camera, we use the Azure Kinect camera's specifications. It has a horizontal field of view of 79 degrees, a resolution of 640 x 480, and depth sensing is clipped in our simulation from 0.5 meters to 6 meters because Kinect is supposed to work in that range. To define the success, we have some rules about what locations would be considered success for the agent. So first of all, the location must be within, must be navigable by the agent. Then the location should be within 1 meter of the bounding box of the instance that you're looking at. The object should also be visible from the location that you're looking at. And finally, the agent should reach within 0.1 meters of one of the instances of the object. The main metric that we use for comparing different methods on our task is SPL, which stands for success weighted by path length. This particular metric not only considers the success of the agent, but also considers how efficient is it in reaching that particular goal location. In this version of the ObjectNav challenge, we release a new dataset. It's called HM3D SEM, and we use the 0.1 version of the dataset for this version of the challenge. This is the largest ever dataset of semantically annotated 3D indoor scenes, consisting of 120 scenes with dense 3D annotations that were created by more than 12,000 hours of human effort. Here are some of here is one of the scenes from the HM3D SEM dataset in a dollhouse view. On the left, you see the RGB render, and on the right, you see the instance annotation of the objects in the scene. Here are some images of the annotations from three different scenes. Looking at the categories from HM3D SEM V0.1, we see a lot of diverse objects of different shapes, sizes, and where they're located. And there's also a good long tail distribution of objects in the scenes that we release. In terms of the categories that we use for our version of the ObjectNav task, we consider 6 core categories, including bed, chair, plant, sofa, toilet, and TV or monitor. We create episodes for these tasks with varying levels of difficulties and a good distribution of goals for the 6 object categories. And we divide the scenes into splits of 80 for training, 20 and 20 for val and test. Now, let's look at some of the stats for the Habitat Challenge. This year, a total of 54 teams participated in the challenge. This is much higher than the previous years, where in 2021, we saw a participation from 45 teams, and in 2020, from a total of 27 teams. We saw a total submission of 1,022 to all the phases of the challenge. And this is also much higher than previous years. Finally, a total of 17 teams submitted to the challenge phase of the ObjectNav task. And now we'll see which are the winning teams from this. So the first place for the ObjectNav challenge goes to Team ByteBot with a SPL of 0.35. The team is from the ByteDance AI lab, and their work is titled Integrating Map-Based Methods with End-to-End Learning. Congratulations to the ByteBot team. Their work basically looks like this. So there's sensor readings that are coming from the Habitat simulator, and they basically take the sensors, do semantic segmentation on the RGBD input, and then pass it through the base method and the end-to-end method separately, and then use a simple switch to define which method to use for taking the action. The switching strategy looks something like this. They use from the end-to-end action or the map-based action, whichever works better for that particular time step. We'll look at their strategy in more detail in the coming few slides when I present their video. The second place for the ObjectNav challenge goes to Team Batseed with an SPL of 0.33. Congratulations to Team Batseed. This work was done by folks from Georgia Tech and Meta AI, and their work is titled IRL Nav, Imitation Learning and Reinforcement Learning for Effective ObjectNav. We have Ram today with us, who will be answering questions about their approach after the video presentation. In their work, they take simple policy architecture and train it using imitation learning on human demonstrations, and then use the policy for interactive fine-tuning in the Habitat simulator using reinforcement learning. Now, moving on to the third place. The third place goes to Team Wally with an SPL of 0.3. Their work is titled Using Scene Memory Transformer and Clip, Solving Object Navigation End-to-End. This work is from the company Wally Factory. And basically in their work, they use architecture that takes in observations and other history of observations, and using self-attention, they combine these observations together and then use a scene memory transformer to combine observations from different time steps. We'll share more from them during the video presentation. Now let's look at the SPL for the top 10 teams from this challenge leaderboard. We see that all these 10 teams have SPL of more than 20%. This is much higher than the teams from previous years. We also see that the 4-team Populous loses to Wally just by 1%, and there's a very tight competition between the top 5 teams. Here is the leaderboard with the top 10 teams. You see the Pitebot teams reaches a success rate of 0.64, which is again much higher than the performance reached by agents in the previous years on the older version of the MP3D MP3D scenes that were used. If we sort this leaderboard table by success rate, we see a slight variation in the performance, although it's mostly local. Now, Team Bad Seed reaches the highest success rate at 65%, and Team Whiteboard is slightly lower than them. If we try to compare the success rate and SPL for the different teams, we see a huge gap in performance between these two metrics. The max possible SPL that is achievable for a particular success rate is equal to the success rate. So in terms of efficiency, there's still a lot of room from improvement like the previous years. And finally, looking at the average success per category, we see the average of all the methods together performing mostly good on all these categories. These are usually categories that are present in all the households and are usually present in well-known common sense-based locations. So we see good performance on all of them. Now let's move to the team presentations. I'll be playing videos of all the teams, and we'll have question answering for teams that are able to attend our today's presentations. Let's start by Team ByteDance. Team ByteBot, sorry. Can you hear the video?
No, we can't see the video either. You might need to stop sharing your.
Yeah, right now he's just talking. So
I see. No, I don't hear it.
Give me a second.
Hello, my name is Minzhao Zhu. It's my pleasure.
I can hear it now.
Okay. Let me share the screen again.
Hello, my name is Minzhao Zhu. It's my pleasure to share our method with you. Our method is integrating map-based method with end-to-end model. In object-go navigation task, an agent is required to search for an instance of a given object category in an unexplored environment. Fireworks can be briefly summarized as map-list method and map-based method. Map-based methods extract the features of observations and the target, then feed them into a model to get action directly. Map-based method build an explicit or implicit map and get a midterm goal using a policy. Then a path planning method or learned model is used to obtain an action. We discovered that most map-based methods are data hungry and difficult to learn some behaviors, such as stopping at the goal location. Map-based methods contain explicit spatial information, but require carefully designed strategy under some scenarios like stairs. Therefore, we try to combine these two kinds of method in order to achieve better performance. Our method consists of two branches, the map-based branch and the end-to-end branch. The output of the two branches is selected by the switch strategy. In the map-based branch, inspired by the semantic linking map, we simplify our previous work by using a probability map. Based on the probability map, we select goals with the largest probability and perform path planning to get an action. The probability map is similar to the occupancy map, widely used in robot navigation. Each cell in the probability map stores a logit value. At each time step, we project the result of instance segmentation to that map. If depth is unavailable, we use the view version of that mask. Then we update the logit value on the cell according to the projected object. The history logit is multiplied by a decay factor, which serves as a forgetting mechanism. For example, if a target object is detected, but the confidence score is below the predefined threshold, we cannot determine whether it is a target, but we should better get closer and check. So we update the cell by adding the logit of that confidence score. If a related object is detected, we update the logit according to the confidence score and the relation probability. The relation probability is obtained from visual genome dataset. In the map-based branch, we hope the robot can achieve efficient exploration like humans, so we use the same model and training procedure as habitat web. Our switch strategy is simple. We will use end-to-end action in three situations. The first one is that the agent is stuck or cannot find a possible path. The second is that the agent hasn't found the target object. The third is that all the cells logit are less than 0, meaning that there is no potential target or related object on the map. Otherwise, we use action from the map-based method. The qualitative result demonstrates how our method works. The agent first explores the environment using the map-based branch. Once it detects a potential target object or related object, it will switch to the map-based method, which guides the robot to approach that area and check. If it cannot find the target object, the probability in that area will decrease. Then the agent switches back to the map-based branch and continue exploration. If the agent finds the target, it will go and stop at that object. The quantitative result shows that both map-based method and map-based branch contribute to a large improvement. Besides, after we fine-tune the semantic model in the training set, we also get a huge improvement. That's all. Thank you for listening.
Unfortunately, the authors were not able to join us today due to some time zone difference. So let's move on to the next presentation from Team Betsy.
Hi everyone, I'll be talking about our work IRL-NAV, imitation and reinforcement learning for effective ObjectNav. This work was done with my collaborators at Georgia Tech and Metafair. In this work, we present an approach to combine imitation learning on human demonstrations and IRL fine-tuning for effective object goal navigation. In ObjectNav, the agent is tasked with searching for and stopping at an instance of a goal category, for example, a cushion in an unseen environment. Prior works have shown imitating a large data set of human demonstration leads to state-of-the-art results on ObjectNav. We find combining imitation learning on human demonstrations and IRL fine-tuning leads to agents learning effective object goal navigation. When using on-policy RL algorithm like DDPPO for fine-tuning, naively initializing RL policy using IL pre-trained weights leads to policy failing catastrophically. due to destructive policy updates early on during RL training. To enable successful RL fine-tuning, we use a training regime with sparse success rewards. For fine-tuning, critic weights initialize close to 0, a two-phase fine-tuning setup with a critic learning phase where we roll out trajectories using a frozen policy that is pre-trained with IL and use collected experience to learn a critic, followed by interactive learning phase where we fine-tune both policy and critic until convergence using experience collected online. We find that naively switching from phase 1 to phase 2 leads to policy failing catastrophically. To remedy this issue, we propose a learning rate warm-up and decay schedule, where after the critic learning phase, we linearly warm up the LR for the policy and decay the LR for the critic to a fixed value. Once both critic and policy reach a fixed LR, we train the policy till convergence. We use CNN plus RNN policy architecture for our experiments. Specifically, we show results using OBRL RGB architecture, which uses RGB only input with pre-trained visual encoder in addition to GPS plus compass and goal category embedding. Compare OBRL RGB to a prior work which uses an explicit semantic predator. We find that using RGB only baseline with pre-trained visual encoder outperforms an approach that uses a semantic predator by 10.2% on success and 4.6% on SPL. Next, we find that using our RL fine-tuning regime, we improve IL pre-trained Sensec and OBRL RGB policies by 3.4 to 5.6% on success and 5.9 to 7% on SPL. Our RL fine-tuning improvements are consistent on ObjectNav test standard and test challenge split. Our approach achieves 65% success and 33% SPL. Next, to investigate the scaling behavior of IL and RL fine-tuning, we plot human demonstration dataset size versus performance on HM3D while split. We find scaling dataset size improves IL performance, but as we scale pre-training dataset size, the improvements from RL fine-tuning are marginal. We present additional such analysis in upcoming work. Now we take a look at the failure modes of our best performing policy. We find our approach has significantly small number of exploration failures, and majority failures are due to missing annotations. Here's an example of early stopping behavior where the agent reaches close enough to the goal but calls stop action right outside the success radius because it's unable to reach the goal due to issues in CNAV mesh. Next, you can see the example of missing annotation. Here the agent sees and locates the object, goes to the TV monitor, but it fails because the annotation for TV monitor are missing. Our agent also fails an episode where it is required to navigate between floors. Here's an example of agent not finding the bed on the current floor because it needs to navigate to a higher floor to find the bed. We quantify different failure modes by manually labeling 500 failed episodes from our best agent. Of the failed episode, 27% come from missing annotations, 21% require agent to navigate between floors to solve the task, 20% failures are due to recognition failures, so I think we need better recognition systems. 11% failures are due to early stopping, where the agent stops outside the goal success radius due to hard to navigate nav meshes. 9% failures are due to bad nav meshes blocking the path of the agent. 6% failures come from semantic confusion, where the agent confuses the goal object, for example, heading to armchair instead of a sofa. Finally, 6% consists of looping, where the agent loops over the same location instead of exploring, and exploration failures where the agent never sees the object during an episode. Key takeaways from our work are combining large-scale imitation of human demonstrations and RL fine-tuning leads to effective object nav agents. RGB-only policy with OVRL pre-trained representations outperforms prior semantic segmentation-based object nav approaches. Thank you for your attention. My name is Ram, and I'm happy to answer questions over email.
Any questions for Ram?
There's no other ones. I have a quick one. What are kind of the next steps that you're looking into to push performance of this even more? Like, what do you think is the most fruitful for that?
Yeah, so I think the biggest issue that we have right now is the agents mostly misrecognize the object. So recognition failure is like the biggest cause that we can fix right now. So that is one thing we are working on. And the other concern is like most of the times these agents like collide into objects, which makes navigation like difficult to some objects. For example, the episodes where the agent gets close enough to the object but doesn't reach the goal, there it most of the time just runs out of the episode limit because it keeps colliding into some object. So making sure they don't collide enough and are better at recognizing are the two areas that we are focusing on right now.
Cool, thanks.
Anu, did you say we lack time?
Yeah, you can go up until 4.
Okay, it's like 5 minutes left. So
Yeah,
move on to
I don't know what happens at 4 with the Zoom link.
Okay. Yeah. Final presentation from Team Wally.
Hi everyone, we are robotics engineers from Wallet Factory. I'm glad to present you our work in Habitat Object Navigation Challenge 2022. Our task is that the agent is given a Go object category, for example, bed, and it must navigate to any instant of the Go category in the house and choose to stop at a Euclidean distance less than 1 meter from that instance. There are 6 Go categories, which are chairs, sofas, plants, toilets, bed, and TV monitors. The observation we can get are RGBD, noiseless GPS, and yaw angle. There are 4 discrete actions which are moving forward by 0.2 meters, turning left or right by 30 degrees, and a stop action. The navigator is tested in an unseen environment, so the algorithm must have ability to generalize. To solve this task, we choose to use end-to-end reinforcement learning. This is our model architecture. We think it is essential for the network to have long-term memory, so we choose to use the memory transformer. The observations are separated into 2 groups. The first group is fed into transformer encoder. The second group observation includes some historical information and key observations such as Go. We use the pre-trained clip VIT encoder to encode images into features, and the weight of this part will be fixed during training. In each step, the image feature, one hot Go, one hot action, and the normalized position yaw will be passed to fully connected layers separately. And then their outputs are fed into a multi-head self-attention block. This is designed to extract some cross-information among different observations. Then the outputs will be concatenated together. In the second group, we make some maps using depth camera, position, and compass. The map grid resolution is 0.25 meters. After concatenating the feature, we use a similar structure proposed in Steam Memory Transformer. We use a DAC to store a sequence of such embedding for 128 historical steps. We also separated the policy for stop and other actions, so the agent will perform better in stop. Comparing to other teams, we have a relative low ratio of SPL to success rate. We suspect the reason is that our agent learned to move forward in a non-electoral way. More specifically, when passing a door, instead of turning right by 30 degrees, our agent will first turn backwards to the left, take a few steps back, and then do a 150-degree left turning and then proceed. We managed to solve this issue by applying a reward that punished this type of behavior, but failure to submit the new policy before the competition deadline. So we don't know if this will improve the SPL to success rate. Besides, in most of the failure cases, the agent is stuck in endless loops in small area. We found that adding trajectory map observations can alleviate this problem to a limited extent, but a more effective mechanism is needed to solve this problem. We also try to substitute the same memory transformer for STM and it keep the other parts unchanged. We find out transformer performs much better than LSTM. Even in training set, the LSTM cannot achieve 50% success rate. Thank you for listening.
Okay, let's quickly try to look at some emerging trends based on those presentations that we saw from the winning entries. So first of all, we saw that the top two teams were using human demonstrations. Badseed used it much more than Whiteboard, but there's some good trends there. Then we saw a combination of complementary techniques by a lot of the approaches. Bytebot uses a combination of mapping-based method with end-to-end method, and Badseed combines imitation learning with RL. Then we also saw reliance on using pre-trained vision encoders by Badseed and Wally. Badseed uses vision encoder trained on images from Habitat, and while Wally uses the flip encoder. Finally, we also saw some introduction of transformer for long-term memory in ObjectNav task by Wally. Let's see where all these improvements lead to in the next version of the ObjectNav challenge. Now, let's quickly think about what's next. So we have the version 2.0 of HM3D-SEM. It has improved annotations. So you heard from Ram that there were some problems in annotations for the version 1 of the dataset, which are solved in this new version. It also has a lot more scenes, so 216 in total, which is nearly 100 more than the version 1. We also have better episode data distribution, which we saw led to improvement in the performance of RL agents on the validation and test set. And we also have more scenes coming on the way in the future. Here is the QR code if you want to look at the HM3D-SEM 0.2. Finally, what could be possible next steps for ObjectNav? Where could the field be heading? And this is my personal insights, and you feel free to use them or ignore them. So first of all, we could definitely try scaling on the largest ever ObjectNav scene dataset. Hint, it's HM3D-SEM v0.2. Secondly, we could see some more work in open vocabulary ObjectNav. We saw one work coming out from Dhruv Batra's lab this year, and I hope to see more of that in the next year. And finally, we could also try to do some sim to real transfer of ObjectNav agents. We saw some negative results from a recent paper that was posted on arXiv, but let's see how this field goes in that direction. Finally, here are the other organizers of the ObjectNav challenge for this year. I thank them for all the work that they did in the successful organization of the challenge. And I also acknowledge the work that Eval.ai is doing for making it easier to post challenge in the internet. And I thank Meta.ai for sponsoring our infra costs. Thank you everyone for participation. And here is a link for our website for your perusal.